We're going to focus today on section 7b, which is all about polyatomic ion naming. Now, the nice thing about this section is that you really don't have to learn anything new compared to 7a. It's going to deal strictly with ionic bonds. We just have to add a little bit to it. I highly recommend that you have your polyatomic ion chart open while viewing this. Alright, so to begin with, let's just do a simple example that will illustrate something that we've done before. So, for starters, we're going to bond with something simple like, say, potassium. Now, we've known time after time that potassium, being an alkali metal, just has a +1 charge, so I'm going to go ahead and label it. Now, in addition, let's pick a polyatomic ion that would readily bond with this. In this case, I'm going to pick out hydroxide. Now, polyatomic ion, as you may remember from your previous assignment, means many atom ion. Poly always means many. So what we're looking at here is that this charge, this -1, is seen throughout the entire molecule. So polyatomic ions themselves are composed of covalent bonds between their structure. So the oxygen-hydrogen in this case is bonded covalently. But due to an uneven distribution of electrons, there is a negative charge on it. -1 in this case. We just don't put 1s for charges, just like we don't for subscripts. So this entire structure is labeled as a -1. So as we've seen previously with ionic bonding, it's simple enough. You just put them together. KOH would be the proper chemical formula. Next, as usual, we are looking for a name. And it's just going to be exactly how it looks. It's potassium hydroxide. There are no changes to a polyatomic ion's name, even when chemical bonding. So remember, "-ide" only substitutes the original suffix if you're doing a singular element, but we're not in this case. It's an entire polyatomic ion, so the name stays consistent. Let's look at another example. In this case, we're going to do calcium. Of course, that is an alkaline earth metal, so we know it's +2. And with it, I'm going to say, let's do chromate. So I've already got the charges listed up, and as usual, they're going to cross and switch, and then simplify because this is still ionic. So this will simplify down to a 1-to-1 ratio. So it's just CaCrO4. That will just have a simple name of calcium chromate. And there you have it. Alright, let's put together another example. And this time I'm going to choose acetate. Now, if you're looking at your chart, you may notice that there's more than one way to represent acetate. This one is actually much closer to its structure, but you can also represent it as C2H3O2 1-. Either way is acceptable, but this way is slightly more correct. So that's the way I'm going to do it, but on any future quiz or assignment or test, either way will be counted correct. Meanwhile, I need a cation to go with this, and I'm going to do copper in the +1 ionic state. So, in this case, I hope you remember that cations always have to go first. So, I'm not changing anything, I've just reversed the order And there is my compound. Now I need a name. Previous rules still apply, so since copper is a stock metal, since it's found in the transition block, I need to have my Roman numeral. Copper 1 acetate would be correct in this case. Alright, let's put up another example. And in this case, I'm going to say I want to bond chlorine with, let's pick a different type of ion this time, and I'll go with ammonium. Now, chlorine is a halogen, so we know what its charge should be, usually -1. Go with that unless I tell you there's an exception. There's no exception this time. Now this one's a little different because we've got a cation that's a polyatomic ion this time, so that one's going to have to go first. So let's put it up. We still have a 1-to-1 ratio. NH4Cl. What is the name? Well, we'll start here. That, of course, according to your chart, is ammonium. What about second? Now this time we're going backwards a little bit. We've got a singular element as our anion, so we have to go back to our original rules. This will change the suffix, so this is ammonium chloride would be the correct name. Now we've done a lot of examples so far with a 1-to-1 ratio, but what happens when that doesn't fit? Well, let's take a look. This time, I think we're going to do cesium. Of course, cesium is an alkali metal, the usual. And this time, I'm going to say, let's do carbonate. Alright, so as usual, we'll take our charges. We'll identify them here. Reverse them. So, cesium will get 2 items, carbonate will get 1. So it's just like how we've always done it. We can check our answer. What is +1 multiplied by 2? It would be +2. There is only one carbonate. Now, one thing that's very important to point out here is that the subscripts that come with a polyatomic ion must never be changed. Period. If you change it, then you have changed what the ion is, and it is no longer the same thing. So don't ever do that. You have to view these ions as one complete unit. So, how many carbonates are there? There's only one. 1 times -2 is -2. So this is a valid compound since it's balanced out to 0, like it should. Let's get a name. We know ionic naming, so in this case, we'll do cesium carbonate. And there we have it. Let's do a further example of that type. Let's see. In this case, I think I'd like to go with phosphate, which is your only -3 ion. And also keep in mind, it's acceptable to write these as either number first or sign first. They mean the exact same thing. It does not matter which way you put it. I'll go with this way for right now. Alright, now let's say we'll do vanadium with just a +1 sign. Alright, so we've got our items ready here, and we'll do our usual. We'll reverse them, but I've got the cation second, so make sure it goes first. It'll just be V3PO4. that would be valid. 3 and positive 1 equals positive 3. Only one phosphate and negative 3 equals negative 3. This would balance out to 0. So what would the name be? Well, be careful because this time vanadium is a stock metal, so I've got to get my charge on there. Vanadium 1 phosphate. Now, this is all well and good, but we haven't really seen an example yet of what happens when you have more than one of the polyatomic ions. So let's go ahead and do that now. Alright, in this case, I'm going to choose to put magnesium with hydroxide. Now, hydroxide, if it's not complete, if you don't have the sign with it, because otherwise it wouldn't be an ion. As for magnesium, well, it is a alkaline earth metal. Those are always the same. So as you can see here, we would be reversing our signs as usual. So magnesium would get a subscript of 1 and hydroxide would get a subscript of 2. How do we represent this? Here is the appropriate way. If you have more than one of the polyatomic ion in your chemical formula, you must use parentheses to illustrate that. This shows that the subscript is spread throughout the entire ion. If you have no subscript, you cannot put parentheses. It will be incorrect. So parentheses, like Roman numerals, are an either you must put it or you cannot put it. So don't fall for that trap. Alright, let's get a name on here, and it's just exactly how it looks. It's simply magnesium hydroxide, because there are no alternatives for the chemical formula for this substance. Let's do another example just to be safe. Let's say we're going to put let's do an example of reversal this time. I'm going to say I've given you the chemical name of scandium 3 permanganate. Now, just do like before. You can check the charges just by looking at it. So, scandium obviously is plus 3. I see that right here. Permanganate is a negative 1. Why do I know that? From the chart that needs to be memorized. So, reverse them as usual to illustrate subscripts, and it would become like so. SCMnO4 taken 3 times. This will balance out if you check the charges. Let's do another example. In this case, let's say we're going to do yttrium of the plus 3 variety, and I'm going to say thiosulfate. Alright. Reverse as usual. So this one's a little different in the fact that both items are going to get subscripts this time. And we can tell by looking at it that the yttrium will get 2, and the thiosulfate will get 3. Both of these, when multiplied out properly, will add up to charge signs of 6, and they will cancel each other out. Let's get a name up there. Yttrium 3 thiosulfate. And it's done. Alright, let's do another example. I'm going to give you a name again, or rather, this time, let's give you a formula and see if you can figure out what the name should be. Okay, so I see titanium and I see carbonate. So let's check. How does this work? Well, carbonate is a -2, but we don't know what the titanium is yet. We need to figure that out. How many carbonates are there? There are 2. What is 2 multiplied by -2? That is, of course, -4. There's only one titanium, so it must be able to perfectly counterbalance the carbonate. So this must be titanium 4 carbonate. And there you have it. Now, sometimes you might run into situations where it seems a little confusing. The best example of that is when you come up with the polyatomic ion peroxide. So let's take a look. Peroxide is O2, 2 negative. Now, let's see how this works when we do something like, say, potassium. Now, let's do lithium. Let's do lithium. Lithium's an alkali metal, +1. So you have to reverse. Lithium gets the 2. I'll put that down. Peroxide gets the 1. But there's a 2 already as a subscript in the peroxide. Remember, you cannot change the subscript on a polyatomic ion, otherwise it ceases to be the polyatomic ion. But there's only one of them overall, so I don't need any parentheses. This looks like something that you should simplify if we were going by normal ionic rules. But can I? If I did simplify it, would this still be peroxide? It would not. So this is an example where you have to leave the subscripts as you see them, even though it's ionic. And finally, a name would be lithium oxide. Nope, it would not. I'm not thinking. Lithium peroxide, excuse me. Lithium peroxide, because lithium oxide would have been Li2O. Alright, now, if you look at the bottom of your polyatomic ion chart, you'll see a special one that follows X rules or halogen-based rules. So what you notice is that all of the halogens, minus astatine, because it's really not going to factor into this, including fluorine, chlorine, bromine, and iodine, follow the same rule for their polyatomic ions. Namely, if you have a single oxygen on it, and all of these, meanwhile, only have a -1 charge, then how you name it is, it starts with a prefix of hypo, you put the meat part of the element, like in fluorine, it's fluor, and then the suffix becomes -ite. And that would be the same case. If we had chlorine, it would be hypochlorite. Bromine, hypobromite, and iodine, hypoiodite. If you have 2 oxygen, let me get that on there. And again, 1 negative. All of these have that charge. Then you drop the hypo. It's just, in this case, bromite. If it was fluorine, it would be fluorite. Chlorine, chlorite, iodine, iodite. Okay, moving up to the next one. Let's say we'll do 3 oxygen. Now the suffix changes to 8. Chlorate. For fluorine, fluorate. Bromine, bromate. Iodine, iodate. And finally, one last one, we will do 4 oxygen, but still the same charge. This adds a prefix of per onto it. So this would be per iodate. Fluorine would be perfluorate. Chlorine perchlorate. Bromine perbromate. So this one is a little simple in that you can just memorize the pattern for all of the halogens, but please do not get this confused. This only applies to halogens. If you try to do it with something like sulfur, you're going to get messed up, because as you might notice, this is just sulfate, not persulfate, and it also has a different charge. But you notice a pattern that ite always means 1 less oxygen than 8. And then you get messed up where these rules actually do apply to things like nitrogen, where you have nitrate and nitrite, but it doesn't apply to sulfur. And then it does apply to things like carbonate, except for the charge. So be careful. Really only follow this for halogens, and if you want to consider it, nitrogen as well. So let's see a quick example of where these are seen in practice. Let's say I've got this compound. Well, that would simply just be potassium hypofluorite. Let's do another example. I'll say that you have the formula. What would this be? I see 3 oxygen, and that means 8. So it's just going to be calcium iodate. Remember, we need that 2 there to balance the -1 on iodate compared to the +2 of calcium. We can wrap up with a couple more here. Let's say that I'm going to do, I'll give you the name of chromium. And we'll do with chromium 3 chlorite. What would the chemical formula be? So chromium, now chlorite is a -1, so I won't put a subscript for chromium. Chlorite is ClO2, 1 negative, and if there's a 1 negative charge at a time, we need 3 of them to balance out chromium's +3. I'll do one more. We'll say strontium is bonding with this guy, and there's 4 oxygen, so that makes it perbromate. Strontium is an alkaline earth metal. So there you have it. Let's put it together. And what would the name be? Of course, it would be strontium perbromate. Alright, so really that's how polyatomic ion bonding works in a nutshell. The last thing we need to cover is how acids work. Now you'll notice that there is a chart at the bottom of the pages on the polyatomic ions that tell you how acid naming works. I'm going to give you a few examples here. So first off, if you memorize that I ate organic despite poisonous acid, this is a little bit of a mnemonic that'll help you remember the pattern. So first off, if you have a singular element, now acids are often characterized by beginning with hydrogen. If you have just a singular element, it's quite simple. You put hydro at the start, you do the main part of the element name, but you change it to ic, and then you add acid. So really, there's few times that this is going to come up. In halogens, you have hydrobromic acid. Let's say it was HCl. That would make it hydrochloric acid. In other cases, let's say you had H2S. We know that would be the formula because sulfur is a -2 and hydrogen is a +1. That would just make it hydro what? Hydrosulfuric acid. Alright, now coming back to this page, if the acid ends in ate, change the suffix to ic and then add acid. If the acid ends in ite, then change the suffix to ous and add acid. So let's see a few comparisons here. If I have H2SO4, naming it by regular convention, it would be hydrogen sulfate, because we know that from our polyatomic naming. Since this ends in ate, it would become sulfuric acid. Ate becomes ic. So there's that. However, if I was instead doing H2SO3, then that would end in OUS, since this ends in ite. So this would become sulfurous acid. Remember, hydro only comes in if you've got a singular element as the anion. Not happening here. Another couple examples. If I had HNO2, well, normally we would have named that as hydrogen nitrite. So since it ends in ite, this would be nitrous acid. One more. I bet you can probably guess what I'm going to do. If it's HNO3, this would be... That doesn't look like a very good 3, does it? Let's fix that there. HNO3, that would be hydrogen nitrate. So this would become nitric acid. This pattern will just go on no matter what you do. So there's really only 3 acid naming rules. These two, and then adding hydro if it's a singular element. So let's wrap up with just a couple more quick examples. What would phosphoric acid be? Okay, let's check. Ic means 8. So this would be based on phosphate. Well, phosphate is PO4, 3 negative. Well, how many hydrogens would balance that out? Probably 3. H3PO4 would be phosphoric acid. If I gave you H2CO3, what would it be? CO3 is carbonate. 8 ends in ic, so carbonic acid. Okay? This can also apply to the X or halogen rules. Let's take a look. I'm going to use the bromine as an example. If I had HBRO, well, normally this would be named as hydrogen hypobromite. Ite changes to OUS, so hypobromous acid. Add an oxygen, what do you get? HBrO2. Now it's just bromous acid. Okay? Moving on to three. Now it becomes hydrogen bromate. So now it would be bromic acid. And to complete the pattern, we will do, of course, HBrO4. Now remember, all of these X rules, or halogen rules, always have a -1 as their charge, so they're only ever going to have one hydrogen with them. That would be per bromate if we were looking at just the ion. So, per bromous acid. And that wraps up both ionic, polyatomic ion to be specific, naming and formation, as well as acid rules.